Can everybody hear me up there? Good? All right. Finish taking the midterm, let's go over the solutions. It was intended to be a relatively easy test. Everything came straight out of the problem sets as promised. Problem number one, describe, if it exists, a data structure that can do delete and add and min in constant time each. How many say there is such a data structure? How many say no, there isn't? Okay, good. So the majority got it right. What's an easy way to prove that there isn't such a data structure? Most of you said it. Yeah. Yeah. So the lower bound is based on, in one word, sorting. Yeah. If there was such a data structure, you can simply use it to insert all the items of an arbitrary unsorted list, find the min each time, print it out, or store it in an array, whichever one you like, and then delete it, and repeat that. Find the min, print it out, delete that, find the min, print it out, delete that, and you'll be printing it out in sorted order. But you know sorting takes n log n time, so this data structure, if it existed, would contradict the fact that sorting has to take at least n log n time, because this would sort in linear time. How many understand this argument? Classical lower bound argument. Any questions about that? Okay. So, easy problem, right? Next problem. Which grows faster, log of log star or log star of log? How many say log star? Well, let's not be presumptuous. What is log star of something?
Repeated logs.
Repeated logs, and the answer is how many times you have to make the logs over and over and over again, the log of the log of the log of the log, until it vanishes. So it's a very slow growing function. Because the log star of a Google is only a few digits, a very small number. So what's larger, log star of log or log of log star? How many say log star of log is smaller than the other one? Log star of log. How many say the log of the log star is smaller than the other one? Yeah, that's true. Why? Intuitively.
You can put n as repeated powers, and the log star of log grow linearly, log of log star grow in a logarithmic way, so
Yeah.
fine.
So basically, if you take the log of something, and then you take the log star of that, how would that compare that to if you just took the log star without taking the log first? What's the difference in these two quantities? The log star or the log star of the log? How much would they differ, these two quantities? By one, right? But the log of the log star is still logarithmic in the log star. However slow the log star grows, the log of that is still logarithmic in that. Doesn't differ by one. It's log. So these two are exponentially far apart. One is exponentially larger than the other. How many get that? So it's a huge difference between us, not even a small difference. Any questions about that? Again, a pretty straightforward exercise in asymptotics. We just finished about a third of the midterm in 5 minutes. Interval intersection. You have a bunch of segments on the real line, and you want to determine if any two overlap, if any two segments overlap like that or not, if they're all disjoint segments, not overlapping segments. How fast can you do that? Asymptotically. And log n, that's correct. In one word, what's the technique? Sorting. Yeah. Now you see why we harp so much on sorting, or, ad nauseum, because sorting is a subroutine in almost everything else you do. In particular, let's nail down the details. So what about sorting? How do you sort here and in what way to get this done? For every segment, what do you sort for all the segments?
Starting point.
Starting point and even the ending points. You can sort the starting points and ending points and sort it all in one big list. And then what? Go through all the sorted starting and ending point, make some sorted order. And what do you do?
And you check that the starting point of the second one is before the ending point of the first.
Yeah. So the first thing you better see is the starting point of something. And the next thing you better see is not the starting point of something else, not the ending point of something else, but the ending point of the starting point that you just saw a minute ago. And you just keep going. And that's how you can confirm that all the segments are disjoint. If they're not disjoint, a starting point and ending point will be mixed with the starting point and ending point of another segment, and they'll be out of whack. So the starting point, all of a sudden another starting point without the ending point first. Okay. Good. You good on that? All right. Any questions about that? Again, an easy problem. Right? All right. Number 4. Devise an optimal algorithm to compute the area of a given non-convex polygon. I could have even asked you on the last problem, prove that your algorithm is optimal, that n log n is optimal, or give an optimal algorithm. I just said algorithm. You can actually show that n log n is optimal. I'll let you think for extra credit about why the algorithm you just mentioned is optimal asymptotically, why you can't do it faster than n log n. So that's extra credit. I didn't want to put that on the midterm because, my gift to you. But it's not that hard. It's just a lower bound proof that matches the upper bound of n log n. All right. How do you compute the area of a non-convex polygon? First of all, let's say you're not sure how to do that. Then what subproblem would you solve instead? Convex polygon. And that's relatively easy. If you have a convex polygon, so here's your convex polygon. How would you compute the area for that? Triangles, yeah. Which triangles? I mean, any set of triangles. You pick a segment and just draw all the triangles, and then compute the areas of all the triangles, and add them up. That's it. That's convex polygon. That's easy. By the way, how do you compute the area of a triangle? If I give you the 3 sides of a triangle, how fast can you compute the area of a triangle if I give you the triangle, either by 3 vertices or the lengths of the 3 sides? Constant time. How many you actually have to do that? Constant. There's a formula that does that, or you can use some other trick. But that's doable in constant time. So that's for convex polygon. What if the polygon is not convex? What if it was something like that, non-convex? How would you compute the area now? You can still do triangles. But if you try to triangulate this non-convex polygon, triangulating a polygon is actually a very hard problem if you want to do it in linear time. If you want to do it any old way, don't care, it's easy. Doing it inefficiently is easy. But doing it in linear time is a trick. And I asked for an optimal algorithm here. So that this word here makes the problem not trivial. It's got to be optimal. If I just said any old way, that'll be a lot easier. So you could triangulate arbitrary polygons in linear time, but it's a very complicated, algorithm. There was a paper in the early 90s that actually finally solved it after many years. It was being open a problem. It's like 30 or 40 pages long to describe the algorithm. It's not a pretty sight. But if you could manage to do that, say like this. Oh, thank you. You wanted to do it like that, you can do the same trick as earlier. But this is hard to do in linear time. So what else can you do? How many solve this problem in linear time, by the way? Okay, half the class. So this is probably the first challenging problem that we've seen so far. And probably the only one in the exam that's not trivial. Of course, this was on the problem sets for the last 3 months. And hopefully you would have seen and solved it before the exam. So let's say, just like here, when we start from some vertex and we sweep to the right, and we hit the first vertex here, there's a triangle, we compute that area, fine. There's another triangle, and another triangle, and another triangle. And you can think about it as a sweep line algorithm that just goes through the triangles here. What if you do the same thing here? You start at some point, say here, and you compute this triangle, and then you have to keep sweeping, but now you're sweeping backwards. So sweeping forward like we did the other one, now we're sweeping back, and now you're computing this triangle, the exterior triangle. And now you're sweeping forward again, and you're computing this triangle here. And you keep going. Which triangle is this? It's the triangle between this line and that line, between the previous line and the next line. So every time you sweep, you get one more triangle. How many can see that? Okay. Now you can't just add them all up like we did a minute ago for the convex case, because why? One word. You just add them up. What gets in your way? Double counting or overlap, right? But what can you do? Subtract. Obviously, subtraction will come in handy. Yeah. So whenever you go to the right, add. When you go back to the left, subtract. Because when you keep going to the right, you'll be adding again. And if you keep doing it, add, subtract as you go left and right respectively in the sweep line, you'll get the right answer for the area. By which principle? There's a name for this principle. We've used it before. Inclusion-exclusion principle. Right out of Polia's book that I keep telling you to read. Okay. How do you see the solution? Any questions about that?
Question.
Yeah.
So to deduce where assuming the vertices in order, right?
Yeah, because it's a polygon, so the vertices have to be given in order. If they're just giving us points, you don't know which polygon it is. Completely ambiguous. Because there are many polygons through a point set. Question.
Can you talk about why this is correct a bit more? Because I don't really remember the inclusion exclusion.
So inclusion-exclusion means if you double count something, you have to subtract it out. So remember when we did range queries, range counting, we computed all the numbers of points in rectangles which were bounded in the origin in one end and at any point in the other end, and each one had a count. And if we wanted to count in an arbitrary rectangle, we subtracted the two sub-rectangles from the big rectangle, but that subtracted that little one in the corner twice, so we have to add it back in. Remember that? How do you remember that discussion? Okay, well, it's been a few weeks, I admit, but still, inclusion, exclusion. Polya talks a lot about it in his book, in read that book. So, inclusion, exclusion. You can also think about examples with sets, right? Inclusion. Let's give a simple example, with sets. The size of the union of two sets is equal to the size of one set plus the size of another set. Correct? No. Why? Because I now counted some elements that may be common to both sets, right? The two sets look like this, right? This is A and this is B. And I can't just add out their sizes. What do I gotta do to get the right answer in this equation? Subtract what? Their intersection. I gotta subtract this area here. That's inclusion exclusion. You include certain things and you exclude other things. Any questions about that? So in pure set theoretic form, that's what it is. All right, now back to this. So you include this triangle by adding it. But the other triangle goes backwards. So you gotta exclude it. Okay. Because when you go forward, you'll re-include it in the sum. Yet one more time, and I'll give you the right count of what's going on here. And you keep going, and if you track this process, you'll see how it works, just like that. And you can do that in linear time, because it's just a sweep, and the polygon has to be linear, given to you in sorted order around the periphery. And it works. So that's just a kind of this is a generalization of the convex case, when it's not just addition, but also additions and deletions and disperse based on what's going on. Okay, any more questions about this? I agree, it's not completely obvious, sure. But given that you got 3 months to work on this, and it was announced over and over again that, problems will be on the exam, and work in groups, and, fair is fair, right? Okay. Number 5, polynomials. Devise a linear time algorithm that's given an arbitrary n degree one variable polynomial computes the value of the polynomial at that place. Right.
We have a question on 4.
Question on 4. How do you say what? That it's optimal? Oh, good. I'm glad you asked. Because we asked for an optimal algorithm. And the one we gave with the inclusion exclusion, sweep line, how fast was that? Linear time. So what's the solution about what's the proof about optimality of this linear time algorithm? Very good question. I'm glad you asked that. You haven't said explicitly, but let's say something.
You have to look at every vertex.
You have to look at every vertex. Because why? What if there's one vertex you did not look at? You did not examine during this sweep, you just ignored it. And you reported that the area is 5 square units. But you ignored one vertex. What could have happened then? That vertex could have been on Mars. Very long distance away. And the area would not be 5 units. It would be many square miles. How do you get that? Yeah. So you better look at every vertex. No algorithm can get away without looking at every single vertex to make sure none of them are on Mars. Because if you didn't look at that vertex, you wouldn't know where the vertex is. And so whatever answer you reported, if that vertex is even further away than it anticipated without looking at it, the answer would be even higher, but it wouldn't be right. Whatever it reported. For example, let's say you have let's say I have 5 bank accounts, and you try to determine my net worth, in terms of all my accounts. And let's say you finish determining my net worth, and you report it to be, $1 million between all the accounts. But you didn't look at one of the accounts. Your estimate is pretty worthless then. You can't have correctly determined my net worth without looking at every last account, because why? If you didn't look at one of the accounts, that account could have made you a billionaire, not a millionaire, and you wouldn't know it. Or worse, you could have had a minus $1 billion balance, a lot of overdraft in that account, and then again will affect my net worth in the other direction. So any algorithm that determines net worth better look at all n accounts. If it's in the linear time algorithm to do that, it's optimal. So this is kind of an adversarial argument of the optimality of the linear time algorithm. It has to look at every data, but you have to say something about that. You're right. Before you pointed it out, we didn't say anything, and silence is not an answer. Any other questions about it? Okay. So, there's a famous method that solves this problem and has a name with two words. Orner's rule. Yeah. How many heard of that? Okay, so you know what the answer is. Good, so that was kind of a gift. Right? You factor out the polynomial, right? So, that's just for the purpose of completion here. So if you have a polynomial, ax cubed plus bx squared plus cx plus d, that's a lot of squaring and cubing and multiplication and addition. But what you can do is start factoring it out. You can say it's x times what? So if you have, you tell me, how do I want to factor this? Yeah.
So you have this x plus b, and so x, another x, with two x sides of x parentheses.
Yeah.
Plus b, and you're factoring out all the x's.
Tell me what to write. I'll write it.
So that
Yeah.
is it going to be ax plus b parentheses x on the outside of that plus b,
Okay. And where's the parentheses?
surrounding ax plus b,
Okay. Now what?
x on the left side plus c. So surrounding those four. And then dx, x on the outside. And parentheses, yeah.
So just do it? Let's see. You have x cubed x here, then you have x squared. You have x times b, so it's x squared b, that's that term here. Then you have x times c, which is this term, and then you have d dangling on the outside, so that's the b. Yeah, and you can do this for any polynomial. And it doesn't even have to be rational coefficients, it can be any coefficients. It works with complex polynomial, complex numbers. And it's just Horner's rule. So how many operations are necessary here? Because if you start squaring by yourself and cubing, there's like 3 multiplications up there. 3 multiplications just to square it, and 2 multiplications to, 2 multiplications to cube it, plus another one. So it's 4 multiplications here, plus 3 here, plus 2. But it's a lot of multiplications, and it grows quadratically. There's tricks to squaring repeatedly, so that you take shortcuts to squaring. You just keep squaring and squaring and squaring the square, and so on. But even that's not, extremely efficient. But here you have how many multiplications and how many additions as a function of the degree of the polynomial. How many additions, how many multiplications in this expression? The degree is k. You have k multiplications and k additions, basically. It's pretty straightforward. So if you implement it in hardware, a polynomial and computation engine or a polynomial evaluation engine in hardware, and often you want to do that. The hardware just needs to do, or even in software, it doesn't matter. Linear number of additions, linear number of multiplications, and linear is actually just n. It's not even 2n or 3n, it's just plain n. So this is called Horner's rule. So it makes polynomial evaluation pretty straightforward. Okay, how many get all this? Any questions about that? Yeah.
I first of all, I was wondering if if there's another valid way to do this, like if you have a polynomial structured just like that up there, you'll have a linear number of terms plus one, and so you have linear plus one terms that you'll have to multiply the coefficient and then the exponent term by, and so
Yeah, he's making the point that there's other ways to do it, and he's right. Right? You can start with x and multiply by the c. So keep the x as a separate variable, and then multiply the x by itself, by another x, and get the x squared. Then multiply that by the b and add that, and then multiply x by another x, getting the x cubed, and multiply that by the a, and then add that. Yeah, so you can do it that way. Essentially, you're doing this, but from a different direction. Okay. You're multiplying, then you're adding, you're multiplying, then you're adding, which is what we're doing here. Multiplying and adding, then multiplying, then adding, then multiplying, then adding. But yeah, you can do it, whichever order or way you want. It still works, and it's still linear time, and it's still optimal. Why is it optimal? Same question as a minute ago. Why is n multiplications and n additions an optimal way to do it?
for the same reason.
For the same reason, because if you miss one of the terms, you don't look at one of the terms, and there's n terms, that term could be a googolplex and you'll never know it. And the answer would have been very different. Or it could be minus a googolplex and you wouldn't know it. So the answer will either be too high or too low. And you'll never know because you didn't look at that one missing term that you glossed over. So you gotta look at all the terms, and so linear is optimal, yeah.
Will you accept any answer that's asymptotically linear?
Sure. Yeah, I mean, there's lots of other ways to approach it. He named another way, and there's lots of other ways. Sure. Yeah, we're pretty lenient in credit. Even if you didn't get the right answer, but you tried a lot of things that didn't work, but you were very diligent about it, and you almost got the right answer, or you were on the way to getting the right answer, or maybe we'll give you some credit. It's not going to be zero. If you leave a blank page, I mean, it's hard to give partial credit to a blank page, like Charles. But other than that, we try to work with you. Right? I want everybody in the class to get A pluses. So help me help you achieve that. Yeah.
What if some coefficients are zero?
What if some coefficient is zero? Very good question. Does this work if one of the coefficients, A, B, and C, are zero? How many say it still works? There we go.
But why it is optimal?
Oh, why is it still the optimal?
Yeah.
If it's zero?
For example, if you want to calculate the x to 4, then maybe you don't use more time.
I see what you're saying. Okay, very good point. He's saying, what if some of the coefficients are zero and you don't need to go through this long series of computations? What if the polynomial was just 8x to the million? That's it. And no other smaller terms. Very good point. You really want to take time, a million multiplications, a million additions, to just compute ax to the million. Excellent. For extra credit, solve that problem. Yeah. So here I was just asking for a general polynomial, not a special case. So when you're talking about a special case, and yeah, now make the polynomial, make the algorithm a function of also how many zeros or non-zeros there are in the coefficients. But I didn't ask for all that fanciness. It's like saying, give me a sorting algorithm that works in linear time if the list is already sorted, or takes longer if it's not sorted. Yeah, well, that's a special case, or a convex Hall algorithm that depends not just on the number of points, but on the output side. And then we had Jarvis's March that does that. So very good question. Extra credit for the whole class. Do that in an optimal way. Yeah.
Can you explain again why it's quadratic if you want to calculate every term?
Well, if you calculate every term like the naive way, without any cleverness or optimization, you compute first x cubed, and then you compute x squared, and then multiply by a, then you compute x squared multiplied by b, and x cubed. So you're doing one multiplication here, two multiplications there, three multiplications there, 4 there, 5 there. So number multiplication is the sum of integers from 1 to n. What is the sum of integers from 1 to n? Quadratic. Remember the staircase? That's what it is. Take the staircase, flip it over, put it on top of itself, you get a square, or almost a square. So whenever you deal with quadratics, think about staircases. And that example with the staircase, you'll never forget. What else? Yeah.
So any effort to follow this one, any effort we do only decreases the basis, right? So the worst case would be this, would be linear. Okay. But in a polynomial only A is non-zero and the rest of zero.
Yeah, well that's what he was saying up there.
The only thing we do is that we decrease the best case, the time of the best case.
Yeah, so what he was saying, what if it's a specialized polynomial that most of them are zero and only one or two terms are non-zero? You can do it you can do it more quickly. You don't have to do it as a function of the degree of the polynomial. But then again, you only have one term, so you better do it not as a function of the degree. Because I can have a polynomial with only one term and very high degree. The degree could be 2 to the 1,000. How would I compute that? How would you compute, x to the 1,000 very quickly? Keep squaring it 10 times. Really, it's x to the 1,024. Yeah. So you don't have to do 1,024 multiplication to compute x to the 1,000. Just take x, square it again. After 10 times, it will be x to the 1,024. So that's a shortcut right there. Successive squaring. That works too. Of course, the problem with successive squaring is it quickly overflows your registers and that kind of thing. But then again, if you ask for x to the 1,000, you're taking a chance anyway, no matter how you compute the answer, because the answer could be too large to contain in a register. But that's a hardware issue, and that's a more mundane issue than just the theoretical part, the algorithmic part. Of course, if you really want to do long precision arithmetic, you do what Mathematica does, or Maple, or any one of those algebraic programs that do arbitrarily long precision. Then you avoid individual registers. You just use large arrays to store digits, and your numbers become very compound, complex objects, and that's okay. You pay for that, but you get huge quantities to work with, and you don't lose precision at all. Okay, what else? So this problem again was meant to be pretty straightforward. It's nothing major here. Sorting. So here I think the problem was to sort numbers in the range 1 through n cubed, right? So if you want to sort numbers in the range 1 to n cubed, think about numbers in the range 1 to n cubed as an squared plus bn plus c, where a, b, and c are all between 0 and n minus 1. So this will be between 0 and n cubed, roughly. How many understand that? Okay. So in other words, I'm representing numbers in the range 0 to n cubed, in this range, representing numbers in the range 0 to n cubed as, really I'm representing them in base n, where a, b, and c are between 0 and n minus 1. Let me give you a more mundane example of this. The number 723. That's a number between 0 and 10 cubed, 1,000. Right? Let me represent it to you in base 10, very explicitly. It's 7 times 10 squared plus 2 times 10 to the 1 plus 3 times 10 to the 0. How many get that? That's called base 10 counting, right? Pretty straightforward. But really, that's what it is. It's the base raised to successive powers times multipliers that are smaller than the base, all added up. That's how we count since prehistoric times. It's not the only way to count. You can use different bases. Here I did it in base 10. There's nothing special about the base. Computers use base 2 with exactly the same principles. You can use base 8 in oct or octal, base 16 in hexadecimal, base 127 if you chose to. The base is arbitrary. How many get to the base is arbitrary? Why do we use base 10? Because we happen evolutionarily to have 10 digits on our fingers. And we even call them digits. Think about that. Fingers. We have 10 on our toes. We could have used base 20 if we were a little more agile and our toes were almost as dexterous as our fingers. Just putting it out there. Or if we had 3 fingers, like some species in science fiction movies, then we'd be counting in base 6. And then that'll be fine. No base is preferential to any other base. In any base, if you want to multiply by the base, what do you have to do to the number? Add what? Add a 0 to the end, or move everything 1 down. That multiplies everything by the base. Works in base 2, works in base 8, works in any base. How many understand that? Yeah, just so it's called a positional number system. The Romans didn't know that, by the way, what we just said. The Romans didn't know any of this. How do they count? Using what's the name of the Roman number system? We call them Roman numerals. Right? They counted as I, IV, V, VI, VII, X, and an I, and an X, and an X, and another I on the other side. And what was 20? And what was 50? What was 100? So how do you take the square root of MVCCIXX? Good luck with that. Okay. So the Romans had a heck of a time doing multiplication, division. Forget square roots. That's one of the reasons they fell. Actually, I'm not being facetious. There were other reasons. They started wars all over the world and antagonized a lot of people and lost a lot of friends. And when you start doing that, you're not going to have a good future. This has always been true. Tell that to our president. But I digress. Because they couldn't do arithmetic very well, they couldn't do higher math very well, the Romans. They couldn't do engineering very well. I mean, they had a good long run at engineering. They did with Pantheon and they did aqueducts. They could do some stuff. But they couldn't create computers. They couldn't send rockets to the moon. They couldn't create automobiles and iPhones. And really, because they had a lousy counting system, they didn't allow them to do math, and all the other science and engineering fields depend on math to flourish and advance and progress. So your math better be pretty effective for everything else to work. Without math, you can't do physics. Without counting, you can't do math. So they were stifled by the number system, and they didn't even know it because it's pretty subtle. How many sort of knew what I just said? See, most of you didn't know it, and it's 2,000 years later. We had a lot of time to think about it. It's true. Any questions about any of this? So we take numbers in the range 0 to n cubed and represent them in base n, which is what we did here. And so a number in base n, its 3 digits, are A, B, and C. And how do you sort numbers in that range then? What sort do you use? Use radix sort, basically. Sort 1 digit, then use the next, sort the next digit, and then the next digit after that. How much memory do you need? How many buckets to do this radix sort of base n? N. So use n memory. What's your total running time? how many passes do you do this radius? So 3. So your running time is 3n. It's linear. What did the problem want? Linear time algorithm. Right? So there you go. And we sort of did this trick, by the way. When did you see this trick last? When we wanted to sort a bunch of ratios. How do you remember that problem? We were doing the same trick there. Okay, so that's just a rehash of something we've seen before. Rectangles. You want to intersect n rectangles, find a mutual intersection of all of them, if it exists, because it doesn't have to exist. The NP. How fast is the algorithm here for kind of straightforward algorithm? Yeah, linear time. How many have linear time algorithm? Yeah. How? Yeah, you can merge pairs and pairs and pairs. But the nice thing about intersection, the operation of intersection is both commutative and associative. How do you get that? So you can associate and commute them any which way you want, and intersect in any order you like. So how about you intersect the first with the second and get the answer? You intersect two rectangles with sides parallel to the axis. What's the intersection look like if it's not empty? Another rectangle with sides parallel to the axis.
Or lines or points.
Yeah. Well, you can think of a line as a degenerate rectangle with a zero side. A point, both sides are zero. So in general, it's just a rectangle. Okay. Next, what do? You just intersected the first pair. Found the intersection. Intersect that with the third. Intersect the result with the fourth, with the fifth. So you don't even have to do kind of recursive anything or get too fancy.
That's all when it's scholars.
Yeah, you just intersect them one at a time with the next, with the next, with the next. Eventually, you'll have your answer. It's linear time. How do you get that? This was a kind of a freebie problem, right? And it also appeared on the problem set for 3 months. Easy though it was. Okay, any questions about this? All right, so the whole midterm you see took only 45 minutes and wasting a lot of time talking about the Romans. So, pretty easy exam, right? All right. So now I want to talk about a really cool topic that's near and dear to my heart, the Turing test. It's really about algorithms, to think about. So the main question is, can machines think? And we've been wondering about that for a long, long time, and I'm still thinking really hard about that. The issue is we don't even know what think means. We sort of know it when we do it, but we don't, in general, cannot define it after all this time. And also, we don't even know what intelligence is in general. And we can't even define what intelligence is. We know it when we see it. We know that a chess grandmaster is intelligent, but a rock is not. You can tell that much. But how do you define intelligence in general? We still don't know. We just know it when we see it, but that's not good enough algorithmically, knowing it when you see it. So you can break down the problem into special cases and ask, can a rock think? This particular rock is a pretty smart rock, by rock standards. Which rock is this? It's a Rosetta Stone. But still a rock. A virus more complicated than a rock, but nobody would argue that a virus can really think at some high level. An amoeba or paramecium, same thing. More complex organisms like flies, you can say they can react, they can forage for food and stuff, but they can't really solve high-level problems like humans. Dolphins are pretty smart, they can do all sorts of clever things, so can chimps, but they can't do calculus that we know of. So, an abacus, a computer, a Turing machine, a supercomputer, these are computation devices that we constructed. The question is, can they think? And that's where the crux of the matter lies. It gets more and more difficult to determine whether these can think until you get to a stage like HAL 9000 in 2001: Space Odyssey. How many have ever seen that movie? The best science movie ever made, science fiction movie ever made. Really ushered in all the other science fiction movies that like Star Wars. You could argue that HAL 9000 could think. In fact, not only could think, it outsmarted the humans that were trying to grapple with it as it was taking over the ship. R2-D2 C-3PO also can think. solve problems, they're intelligent. And so can all these other characters from science fiction movies. And the reason we have to resort to science fiction movies is we don't have demos of them yet, other than movies when they're kind of simulated. And I say yet because we're getting there. Data from Star Trek, Terminators from the Terminator movies, agents from the Matrix. These all can think. Not only can think, can outthink us. They got the better of us in most of these movies. Cylons from Battlestar Galactica, and of course humans can think too. In fact, humans are the benchmark for thinking and intelligence. Because we have no other example, not because we do it so great. We just do it kind of, okay by our standards. But not only that, we make ourselves the benchmark of everything in the universe. But that's just, being infantile of the species. But again, I digress. So it's hard to tell. But Turing, to his credit, wrote a single author paper, just him, and he addressed this problem for the first time in history formally. We've been wondering about this for a long time before Turing, but he actually made headway and contributions to this very deep question. First thing he said is, I propose to consider the question, can machines think? And this should begin with a definition of the meaning of the words machine and the meaning of the words think, which are still fuzzy to this day, especially the word think. So very insightful insight right off the bat. And then he kept going. And by the way, the first chapter or section of his paper is called The Imitation Game. Now we call it the Turing Test. Now you know where the title of the movie came from, The Imitation Game. It was the actual title in real life of the first section of his famous paper that not only talked about artificial intelligence, it pioneered the entire field of artificial intelligence. This paper invented AI. How many of you knew that? Before that, there was no AI. There was math and there was computation. But he ushered in the entire field of AI with this very paper. That's why the movie is called that. So he suggested the Turing test, the imitation game. He said, give it some questions for about half an hour or an hour, question that thing. Who questions that thing? You do. You, the already presumed intelligent entity. And after a while, if you're satisfied with all the answers and you determine that there's intelligence there, fine, that thing is intelligent. So that's sort of the test. You give it the test, ask it a bunch of questions. You can ask it questions about chess or addition. Notice here, it's trying to trick you, telling you to add two numbers together. It doesn't give you the answer in a nanosecond, like a computer would. It gives you the answer after a deliberate 30 seconds of waiting, and then it gives you the answer. Because if it gave you the answer in a nanosecond, you'll know it's not humans. Humans can't do it that fast, or even 1 second. It would be too quick. So it's trying to mimic a human being. And if you give it a chess position, it'll tell you, yeah, it's a mate in two moves. By the way, it can also make mistakes on purpose. Because if you gave it the square root of some million-digit number, and it gave you exactly the answer without any mistakes, that's kind of superhuman kind of performance or achievement, especially if it happened quickly. So it can deliberately not only take longer times, it can actually deliberately make mistakes on purpose to fool you into it, you thinking it's a human, because humans make mistakes too. So that's okay. That could be all part of the dynamics of the test, of the Turing test. So basically, you need to distinguish a machine from a person. So you sit on one side of a brick wall, and you ask the other person from the other side of the brick wall using texting only, and it's easy to text, especially nowadays. You give it questions and you get answers back. And why a brick wall? Because you don't want to be fooled by how that thing looks. You don't want to be biased, whether it looks like R2D2 or C3PO, or just another one of us, or some Cylon or some Terminator disguised as a human. You don't want to be fooled by looks either direction. You don't want to think a Terminator is a human because it looks like it, and you don't want to think that R2D2 is not intelligent because it doesn't look like a human. So you don't want to be biased by appearances. Right? Don't judge a book by its cover, basically. So you just use text, not just looking at that thing that's answering. In some scenarios, a human will identify another human as intelligent. Other scenarios, you'll have a supercomputer that has a super duper AI program in it with machine learning, and it will behave intelligently, and it would fool you into thinking that it's intelligent. So it was the first deep investigation into whether machines can behave intelligently, and it ushered in the whole field of AI, and it decoupled the notion of intelligence from being human for the first time in history. Because before that, we assumed that humans are intelligent, and intelligence means we're human. because everything else around us doesn't seem to be intelligent as we are. So it's basically basing intelligence on input-output behavior, not on appearances or what that thing is specifically. And it's a practical test. You can actually implement this. It's been implemented many times and actually tested. So there's many variants on this test. There's even things like a reverse Turing test and other kind of tests. We'll talk about some of them. Historically, in 1700s, there was this so-called Turk, a mechanical apparatus that seemed to play really good chess, grandmaster level chess. And for many decades, almost a century, toured the world and gave shows on stages, and people thought that there was a chess-playing machine. And it turns out there was a little guy in there that was kind of working the little levers and pulleys and machinery there. And that guy was a grandmaster in chess, and it went on for so many years. I guess they needed a bunch of little guys that could play chess. It went on for a long time, this hoax. So that's one of the earliest kind of Turing tests. They would even open this apparatus one side and then close it and open the other side to show the audience that there's nobody inside. Of course, that little guy would slide back and forth depending on which door was open. So even that was kind of hoaxy. But fast forward a couple hundred years, and people started writing programs that mimic human intelligence. And so one of the first ones was called ELIZA, based on Eliza Doolittle and My Fair Lady, or Pygmalion, Bernard Shaw's Pygmalion play. And it basically simulated a psychotherapist. If you told it, I hate my parents, you would type back to you, why do you hate your parents? What happened? And it would go back and forth. And a lot of people that used it actually felt a lot better about themselves after they interacted with it for an hour. Which kind of makes you wonder what psychologists do for a living. But anyway, and why you should pay them $100 an hour for whatever it is they do. But I digress again. HAL 9000 in the movie was one of the earliest examples of an intelligent AI that can even outsmart humans. And then, so these are called chatterbots, and you see them in chat rooms, and even in dating services. You see these ELIZA-type programs and chatterbots in dating services. Next time you go on Match.com or, OkCupid or whatever these other websites are, you may be being catfished by a bot, by a chatterbot. So be careful. Be careful out there. You may be talking to an AI, not another human being that you're just invading. It's easy to fall into that now because they're so sophisticated. And there's even chatterbot competitions. It's like a Turing test format, and there's people behind the curtain, and they judge whether things are intelligent or not. And there's many of those, and they get prizes, and some of them are very sophisticated. There's a program called LBOT that about 10 years ago won the so-called Loebner Prize. It fooled 3 out of 12 judges. So Turing said you got to be about 30% or better in terms of who you fool in order to pass the Turing test, because you can't fool everybody. Somebody, eventually will out you if they're clever enough and ask the right question. But, out you as what? As a non-intelligent entity, as some machine that is glitchy, rather than trying to determine that it's intelligent when it isn't. And these judges, by the way, are not just, naive people. They're experts on this subject. And they're still getting fooled at the rate of about a quarter to a third. So that's pretty impressive. Just to show you how clever these bots are, this is an actual excerpt from a competition just about 10 years ago with particularly this LBOT robot. So the judge says, what's your favorite novel? And it says, I read telephone books or poetry, blah, blah. And the judge says, typical computer. And the bot tells it, you tend toward generalizations, but I must admit, so do I. Finally, the judge says, what do you think of somebody's enthusiasm for having machines take over the world? And the bot comes back with this line, fix up the world a bit, and then we'll take it over. So that's irony, right? That's being snarky. That's kind of a hallmark, one of the hallmarks of intelligence, being witty, using humor. This actually happened during competition. It's not just a made-up script. So they're getting pretty clever. And there's lots of other forms and Turing tests and prizes and international competitions. It's been going on for a couple of decades now. Some of them have aerial robots roaming around trying to find places on their own without any guidance, just software and hardware combinations. So now we can ask a more clever question than before about all these entities from before. We're not going to ask which ones can think. because we're not sure what thinking means and intelligence means. And now we have an operational Turing test that we can actually implement and apply to these objects. So now we can say which one of these can pass the Turing test, and this question we can easily answer. Right? So which one of those can pass the Turing test? Well, first of all, notice that some of them are software objects. Even the HAL 9000 was not like a physical entity, it was just mostly software with a few servo motors here and there, but mostly software. So was the agents in the matrix and so on. And these machines are all equivalent. An abacus is equivalent to a Turing machine, and a Turing machine is equivalent to a supercomputer. How many understand that? An abacus is just a lot slower than a supercomputer, but can do whatever a supercomputer can do, just a lot slower. And by the way, you need a heck of a big abacus, not just with a few beads. But just so you know, in case you didn't know this, all these are equivalents. I'm drawing equivalence classes here. And of course, all humans are equivalent. Doesn't mean they all have the same IQ. It means they all can behave intelligently as we kind of intuitively understand and define intelligence. And just because a human is paralyzed in a wheelchair doesn't mean they're not intelligent. In fact, this particular human, one of the smartest people on the planet, Stephen Hawking. Right? So you don't get fooled by appearances. You just say which one of these can pass the Turing test if they're behind the curtain. So now that question is a lot easier. A rock cannot pass the Turing test, obviously. Neither can amoebas or flies. Dolphins can't either, not because they can't do some clever tricks, but they can't respond to English queries and text you back. So neither can chimps. And by the way, chimps can still do amazing things. There's a chimp that learns sign language, American Sign Language. It's called Washu. How many heard of that chimp? And he had a vocabulary of several hundred words. And when the chimp was asking for food, he was asking for an apple using American Sign Language. And when he gave him a banana, he said, no, I wanted an apple. I mean, he was very specific. And this went on for years. It was studied with psychologists, and it was an amazing thing that a chimp, a monkey could learn human language. And of course, because their vocal cords are limited and so on, he couldn't speak the words. But sign language they can do because they have dexterous fingers. Parrots can actually speak too. So the borderline starts here at this point. Now, computers, we still don't know whether they can generally be intelligent. We're working really hard on it right now to come up with ones that are smarter and smarter. Machine learning is kind of leading the way now. HAL 9000 was, now he was intelligent. He could pass the Turing test. So can C-3PO and R2-D2. If you interpret the chirps as inputs and outputs, like his buddy did for him all the time. Data from Star Trek, Terminators, Agent Smith from the Matrix, all intelligent, highly intelligent, not just intelligent. And certainly they can all pass the Turing test. In fact, they can do a lot more than pass the Turing test. They can hunt us down and kill us in those movies, and a whole lot more than that. So they're pretty clever. They can pass the Turing test in particular, so can Cylon. In fact, Cylon, how many saw Battlestar Galactica, the recent version a few years ago, not the old one from the 70s. An amazing show. You should watch it. The whole show is about the Turing test. Really, if you think about it, it's filthy. And these sentient entities, not only they were intelligent, not only, of course, they can pass the Turing test, not only they can fool other humans into thinking that they're humans, some of them didn't even know that they're not human. That's how far advanced they were. And of course, humans can pass the Turing test. In fact, we invented the Turing test, so you can pass it. So the borderline area is here. The fuzzy is here, from no, 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 no to a bunch of yeses. This is where we're still not sure what's happening. And by the way, the rest are fictional characters because we haven't even built a machine that passes the Turing test ourselves, and so we don't have anything to do more than that in general. So I'm using fictional characters that we all know and love from the movies to make the points. Okay? So whether something is intelligent, what is intelligence, what is thinking, what is consciousness, we've been contemplating that for a long, long time. But Turing is the first guy that did this formally and came up with the Turing test and looked at the implications of what it means. It's a famous cartoon that on the internet, nobody knows you're a dog. How many have seen that cartoon? So that's about the Turing test again. Right? In the movie Blade Runner, Deckard, played by Harrison Ford, gave some character the so-called void camp empathy, but really the Turing test to see if she's human or not. How many have seen that movie? Again, a beautiful, great science fiction movie, early 80s. And it turns out that she wasn't human, but there was a twist. She didn't even know she wasn't human. She thought she was human. He knew that she wasn't from this test, but he didn't tell her, and eventually they went off into the sunset. So interesting other twists in the middle. So very intriguing movie, and again, kind of based on the Turing test or around the Turing test. There's criticisms of the Turing test. Sometimes it's getting some flack because it's behavioral only. If the person behind the brick wall says that that thing is intelligent based on the I/O behavior, it doesn't tell you anything else about it. It could be a machine, it could be a cyborg, it could be artificial, it could be natural organism, it could be just some mechanism that just happens to give the right answers. So it's a behavioral test. It doesn't test like the essence of what it is behind the brick wall or the curtain. It's comparative. It's not a direct test. It compares it to a human. The object where you're testing whether it's intelligent or not is the result of the test is relative to you, the tester. It's not some objective absolute scale like temperature or pressure. It's all relative to you. So these are criticisms of Turing. But that's the best we got so far, this kind of a test. And sometimes human behavior and intelligent behavior don't always coincide. And if you don't know what I mean, look at what some happens in fraternities and sororities across campuses. And we see some good examples of that. Intelligent behavior and human behavior are not always the same thing. Some human behavior is definitely not intelligent. And some intelligent behavior is definitely not human. Because we have bots and AIs and machine learning algorithms that behave pretty intelligently, but obviously they're not human. So the two things don't necessarily coincide. That's another kind of criticism about the Turing test. And there's a deeper question of whether a simulated intelligence is actually intelligence, or is it something else? And if you can simulate intelligence well enough, does that qualify in itself of being intelligent? And there's something called the Chinese room example. I'm going to talk about that in a second. And people tend to anthropomorphize objects. Some people will swear to you that their dog or cat or parrot or turtle are smart or intelligent. Okay, so people tend to kind of view intelligence onto other things, project it out. And most people are easy to fool. So that's another kind of pitfall about Turing tests. Is you fool a lot of people a lot of the time. So the Chinese room I alluded to, so an example by John Searle from 1980. So here's an interesting twist on the Turing test, or intelligence in general. So there's a person behind a brick wall, there's some machine there that runs a piece of software, there's the code, there's the machine, and you do interaction about intelligence and the Turing test. Let's say this computer here running this code passed the Turing test with that person. So that person, though, is speaking in Chinese, because there's no constraint that the Turing test has to be in English. It could be in any language. Chinese is just defined language as English or any other language for that matter. So this Turing test happens in Chinese, and that machine passes the Turing test in Chinese. So when a question is asked, a reply is received. Now I don't speak Chinese, but maybe some Chinese speakers here can tell me what this says, or it makes sense even at all as a question and an answer. Does it? Not really? Okay. But it's grammatically correct, right? It's a question. So no, not even, okay. Then,
The question is grammatically correct. The answer doesn't really bear meaning.
Okay. So I guess I can't pass the Turing test in Chinese then, but I can in English, so I'm okay. So let's say this happens, and so any question is an answer, and that person is satisfied. There's this intelligence behind the curtain. Now take that scenario and slightly modify it. Take this computer and replace it with a person that would run the code by hand, line by line, go through the flow chart of the code and simulate the code, a person. But that person is not a Chinese speaker. Say he's an English speaker. That person doesn't know a word of Chinese, but they know how to take code and execute it by hand with a pencil and paper. So now there's no computer here, there's a person. And if the person runs the same code, and time is not a factor. So it's running very slow now, but because it's the person running it, but that's okay. Time is not an issue. Take all the time you want. Whenever the person, the tester now in this new Turing test scenario will ask that box the same question as before, it will get the same answer as before because it's running the exact same piece of code. How do you get that? Obviously, there's no change there. And so this person will declare that whatever's in this room, this box, passes the Turing test and therefore it's intelligent. Except that if you look at it more closely, where in this room does the intelligence actually exist? The person he's a person, but he doesn't know a word of Chinese, so he doesn't even understand what's coming in and what's going out as inputs and outputs. So there's no sense of understanding or perception or analysis or, they're just mechanically going through the code, not even understanding what they're doing or what's going on. And it doesn't have to be a person, it can be a child, doing this or whatever. So where in this room is the intelligence? Is it in the code? It's certainly not in the person, because the person is doing nothing but just executing simple lines of code one at a time, like a microprocessor would. So that's the Chinese room scenario by John Searle. Yeah.
I have to correct myself. The answer does make sense. It's ancient Chinese and just not good enough.
Oh, okay. He says it does make sense if you consider ancient Chinese. Oh, or
It's
some
old, so it's like
old school
2,000
Chinese.
years ago.
All right. Yeah. So the Chinese room basically kind of dissects the thing and asks whether the ability to simulate a mind is the same as having a mind, at least functionally or philosophically or morally or ethically or however you want to think about it. That's a very deep question. These are all up for debate. There's no hard, concrete answers to most of these things. And it gives rise to a whole bunch of stuff. There's applications of a human test. Instead of a computer trying to convince a human that it's another human, sometimes a human needs to convince a computer that it's not another computer. That's called a reverse Turing test. Where is this used in real life? CAPTCHAs. You go to a website, you have to prove that you're not another bot, another computer, by doing something that only humans can do, like recognize weird text or solve some math problem or whatever, simple arithmetic. So that's called a reverse Turing test. So it has lots of applications. In fact, in a typical week, you actually are taking reverse Turing tests all the time as you visit websites. How many have done that online? Okay, so you know what I mean. So these are CAPTCHAs. And CAPTCHAs are getting more and more sophisticated because computers are getting more and more sophisticated than algorithms do. And now CAPTCHAs almost have to be like real-time short video clips that move around in real time in tiny little GIFs to be effective, because computers are getting better and better. AI, machine learning is getting better and better at deciphering these CAPTCHAs. There are lots of cartoons about it, a bit offline. As far as robots and AIs, the first robot story was Frankenstein. Actually, there was one earlier than that. Anybody know the story of the Golem of Prague? Nobody heard of that, but know what I'm talking about. Okay, never mind. Frankenstein, you heard about it, I assume. Yeah, good. So that was almost 200 years ago. So the robot was more synthetic, made of parts, human parts and flesh and organic materials, but it influenced all the other AI stories and bot stories and cybernetic organism stories that came after that. Including Terminators and HAL 9000 and Rocky Horror Picture Show. There's even kind of parodies of Frankenstein stories. But Terminator is a Frankenstein story. It's about something that we created that got smarter than us and overtook us, and unintended consequences, and chaos ensues, and a lot of regret on the part of the creators. Which is exactly what the Frankenstein story was about. This is exactly what Terminator is about. This is exactly what Neo in the Matrix is about, and many, many other stories just like that. It's a very alluring motif for not just science fiction, but storytelling in general. Not just unintended consequences, but ethics when you do research and invention and creation, and the dangers of playing God, messing with Mother Nature in various ways. And there's been hundreds of movies about, maybe thousands. Shout out if you recognize any of these movies. We'll see how many science fiction buffs. Which one?
Metropolis.
Metropolis, yeah. 1920s silent film. This one? The Day the Earth Stood Still, which was later remade with Keanu Reeves. There was an old series called The Avengers. Patrick McNee, Diana Reed. I'm giving away my age here, I guess. I've been watching this in the 1960s. This one? Lost in Space, yeah. Danger, Will Robinson. Okay. You know what I'm talking about? Okay. Really good shows. Star Trek, you heard about, Captain Kirk, okay. Well, that's more later and more famous, and that kind of endured the test of time. It had an M5 computer, a sentient computer. Of course, HAL 9000 overshadowed all of them back in the 60s. And, Colossus, the Foreman Project. Which one is this? Silent Running, it's called. 3 little robots called Huey, Dewey, and Louie. And they were the inspiration behind Star Wars R2-D2, actually. That preceded 1977, the original Star Wars film by George Lucas. This are actually the inspiration for R2-D2. Great movie, by the way, if you want to watch it. A lot of these are great movies. This one, Short Circuit. This one, vector graphics from the 80s. Really cool back then. It's before CGI. What was the movie? Tron. How many ever heard of Tron? Okay. This guy's a buff. That's great. Science fiction buff. Saturn V with Kirk Douglas. Whopper. That's a hacker's favorite iconic movie. Which movie? The war computer from War Games. Movies from War Games. Of course, you have RoboCop. You have Star Trek. You have Data. So these are all AI entities. Intelligences. These can all pass the Turing test. And then, of course, Terminators up the wazoo. The old T-100, and then the many quality alloys, the T-1000. The original ones look like little tanks, actually, the precursors to these other Terminators before they made them human-like. But these are all from the Terminator series. Then, of course, not to be outdone, there were women Terminators. Really good TV show about Sarah Connor Chronicles. How many have seen at least some of them Terminator movies? Okay, so pretty interesting. Kind of philosophical, but also kind of thrilling because it's car chases and explosions and gunfights. But philosophically, it's very intriguing. Never mind the explosions and the gunfights. This Westworld, Bill Brenner. How many seen the new TV show called Westworld? That's about AI and the Turing test. The entire show revolving around those concepts. If you've ever seen at the beginning, he looks at the host that's leading him into Westworld, and he says, "Are you real or are you a robot?" And she says, "If you can't tell, does it make a difference?" That's a Turing test, like explicitly right there in that scene. And it's just a beautiful show. Very psychologically intriguing, deep, philosophically stimulating. It's just, if you haven't seen Westworld, you should see it. It's amazing. But the old TV show and the old movie, these bots, later on, these fembots in the $6 Million Man, the Bionic Woman, and later Austin Powers with his fembots, they were all takeoffs on the original Westworld from the 70s. And of course, you got Ash from the Alien movies, Box from Logan's Run, Car, the self-driving car from Knight Rider. Right? How many heard of Knight Rider? Okay, so it's a cult show. Giant robots, and who's this guy?
Grievous.
Yeah, General Grievous. So that because that's good. It's good. Of course, these were Daleks from Doctor Who, right? And of course, you got your Blade Runners, the replicants. Which movie is this? It's actually a movie called AI by Steven C. Spielberg. So the AI is right there in the title. The Matrix, you got these agents, Agent Smith from The Matrix. This was Angelina Jolie started that one. This is iRobot, Will Smith. Cylons from Battlestar Galactica, all forms. They started as clunky, contraptions, and eventually they evolved into something that not only humans can't recognize as machines, but they themselves think they're human. And no discussion of AIs and robots will be complete without the Borg from Star Trek, of course, I included that. And some of them are parodies. I consider the Tin Man from Wizard of Oz to be a robot or an AI of some kind. Your mileage may vary, but which movie is this? Robin Williams starred. Bicentennial Man. Right? Have you heard of it or seen it? Okay. The rest? Yeah, you've got your work cut out for you. And of course, Isaac Asimov wrote the first robot stories in the 1930s and 40s. Before computers were even invented, he actually wrote stories about robots and AI, which was amazing. So he was kind of the master of robotics. In fact, he invented the term robotics. That was a term that he coined, actually, back in the 40s. And he coined the laws of robotics. right? The laws of robotics, a robot cannot injure a human being or cause it to come to harm, but it must obey orders only if it doesn't interfere with the first law or contradicts the first law, and must protect its own existence only if it doesn't interfere with the first two laws. This is a form of programming right here, like logic programming. How many have heard of these laws or seen them? Okay, good. He invented that, and his stories revolved around these laws as part of his subplot. And he made for amazing stories. So the three laws were robotics, and there's Bicentennial Man projecting the laws as he's unpacked and turned on by the family that just purchased him in the movie. And he's kind of showing them how he operates according to his rules. So it's rule-based logic programming, years before computers were even invented in the 1940s, Asimov did that. So he was sort of a computer programmer of sorts. He was a roboticist, really. And then later we came up with Law Zero, somebody, other people, the robot may not harm humanity by action or inaction, and then that superseded the first law. So it's okay to harm a human as long as it saves all of humanity. That takes precedence. And later, some said, why humanity? That's kind of, speciesist. Right? If you're against certain races, you're a racist. If against certain, if you're against certain genders, you're a sexist. If you're against certain species, you're a speciesist. That term is not often used because most people have not evolved to that stage where they can see the generalization of where this goes. But once you do, you kind of cross on humanity, including sentience in general. Don't harm sentient things, not just humans. Because otherwise, you can be accused of being a speciesist. Early days of robotics, these were killer apps. These are actual machines that we have. So they're literally killer apps. These apps will kill you. They crawl around, they have machine guns, they have treads, they have AIs on board, and they go around battle zones like Afghanistan and Iraq and other places, and they do stuff. This original bots, which era is this? This is from a famous war, but how long ago these bots went around? They can do only primitive things, like go in a straight line for a couple hundred yards and explode.
Second World War, right?
Second World War? No, it's earlier than that.
First?
Yes, First World War. You look at their uniforms. These are First World War soldier uniforms. These bots were like roving landmines. It scared the heck out of the enemy because they would move around in some pre-programmed path and then explode. They wouldn't wait for the enemy to step on them or come close. So World War I, 1915, 1918 era, we already had killer bots going around battlefields. Of course, now we have real sophisticated ones that can on their own do stuff. And we can debate, the ethics of it and the philosophy and the danger of it. In the air, you have killer bots too now. You have predator drones. You have Reapers. These fire hellfire missiles that can take out tanks or buildings. It happens all the time. They fly very high and silent, and they can fly for days because they don't have a human payload, so they're not restricted by human cargo constraints. Lots and lots of them. Some are supersonic. They have smart bombs. So these are not movies now. We switch from movies to reality. This actually happens. It's been happening for 10 or 15 years already. It's nothing terribly new. Some of them are dirigibles. They're lighter than air. They're robots. They're AIs. Some of them helicopters. Of course, you've seen the drones that you can buy at Toys R Us nowadays, and even those are very sophisticated. Some of them can be pre-programmed to go on arbitrary patterns, and some of them can be overlaid with software that gives them intelligence. Some of them are armed, even small ones. And it's pretty amazing. Some of them are helicopter types, some of them are tiny. Some of them are the size of insects. I'm showing you scale here. Some of them can fit in the palm of your finger, and they're still flying around doing things, doing surveillance, reporting back data. And usually it's the battery time that limits their flight time to 5 or 10 or 20 minutes, and then they run out of juice. But typically ARPA designs and builds these things. On water, you got more bots, AIs, submersibles. These are all autonomous vehicles. During the Chinese Olympics, they had these robot little boats with machine guns on them patrolling the periphery of the waterways around the Chinese Olympics. Very effective. Again, we debate about the ethics of putting guns on robot ships and sending them off to do things, but the point is, it's capable of doing this. The technology now exists. More submersible, there are bots. Self-driving cars. That was a big challenge in 2005 by DARPA to create the first self-driving car through 100 miles of desert. How many heard of the Grand Challenge and DARPA to create self-driving cars. And at the time, it was a very hard problem. You can see the LiDARs on board and all the radars and acoustic sensors. It's a competition because self-driving cars, we tried to do that for decades. And then DARPA put $1 million prize on this problem. Whoever finishes 100-mile of desert course self-driving by itself, we get this $1 million. So a bunch of teams joined, and nobody won. They all kind of petered out after the first couple of miles. Next year, they doubled the price at $2 million. More teams joined. Based on the expertise of the previous year and the previous teams, they built more sophisticated self-driving cars. Again, this is from 2005, 2006. And a couple of them won the course and got the $2 million prize. But they were very clunky looking, very prototype kind of oriented, lots of parts sticking out, retrofitted on existing vehicles. And, it's, I think about them as touring machines with an O before they do. And that was very cool back in 2005. I mean, it's even cool today. One of these, this one is in the Smithsonian Museum, actually. So fast forward 10 years, now you got the Tesla Model S. It's got autopilot, it's got a lot of AI on board, supercomputer can do 100 trillion operations per second, not billions, trillion. It's got a huge supercomputer on board. So it shows you that algorithms can be beautiful. And to add to that, it can also do 0 to 60 in 2.3 seconds. So not only is it beautiful, it's fast, and you can go 350 miles on a charge. So this is my favorite touring machine. So in fact, I like this touring machine so much that, I actually got one of my own. So that's my touring machine, and sometime during the semester, probably the next few weeks, we're gonna set up a Tesla demo day, maybe on a weekend. I'll drive this beast in there to the parking lot and take rides. And if you never failed 0 to 60 in 2.3 seconds, you're in for a treat. Just make sure you didn't have lunch right minutes before the ride. That's all I ask. And by the way, I'm driving, not you. Although this thing can drive itself. It's got full autopilot, and you'll see how it can just drive itself hands off and does the right thing, stays in its lane, stops at the obstacles, and so on. So we'll do that in a couple of weeks. Okay? And I have more to say about the Turing test and AI and robotics, but we'll continue this next time. Any questions or comments? It's really cool stuff. All right. Have a good
我想买这个玩具，这个得8万。